calculations and instead look at math as more logic and abstract concepts. So here we're going to look at sets with numbers, but you might also have shapes, names of animals, images, whatever. As long as you are clear with what the actual objects and elements are, it's all good. It's just a general pattern and general idea. So for instance, I might have a collection of numbers, say 1, 2, and 3. And to represent them as an actual collection, I put these squiggly brackets and I separate the objects with commas. So 1, 2, 3. This is my collection. I happen to have 3 numbers in it. This is a set. And I might even name it A. Okay. I might also have a set, say, heart plus 8. Let's just leave it at that. So this is a collection of objects. This shape, and 8. And you might choose to, interpret that as a plus symbol, but it doesn't really matter. So we just have an object, and I will call this set B. Okay, so you might get the idea here. And you might have names of something. You might describe a set. So we'll go into some other ideas here, but these are objects. Just want to kind of highlight that. Okay, so these are each elements. Now along these lines, since we were counting these objects, I'm going to introduce the word cardinality. Cardinality refers to the idea of the size of a set. And for these two sets, we can count the number of elements. So here we have 1, 2, and 3 elements. They just happen to also be 1, 2, and 3, but we have 3 of them. And we have 1, 2, and 3 objects or elements in this set. So these sets have the same cardinality. They are both 3. And we represent that with this kind of absolute value sign. It's just the size or the magnitude. Or you might have seen, these straight vertical lines in different contexts. But here, for sets, we're talking about cardinality, which refer to the size of a set. Now, this is just a general concept, so naturally, when we think about cardinality, we can consider the fact that some sets are not finite like that. We just listed 3 elements, and that was our complete set A, 3 elements for set B. But there are some sets that have infinitely many elements. For example, let's say we have the set of even numbers. So how would you represent that? Well, for even numbers, 2, 4, 6, 8, 10, 12, 14, 16, ... might come to mind. But we also have 0, which is definitively even, by the way, and our -2, -4, -6, -8, etc. So you could just kind of start writing some of those and go ... to represent that it goes infinitely large and infinitely negative. If we want to start trying to represent this, I'm gonna run out of room here, this set. So in this case, I'm trying to list out some of the elements in the set of even numbers. When you think about the cardinality of this set, well, you can't exactly, there are infinitely many elements. So when we talk about the size of this, we might compare it, for instance, to the size of another infinite set. So instead of just saying, oh, the cardinality is infinity, well, we could do other analysis and play around with some set theory to consider the actual largeness, the infiniteness of the size of this set. But I wanted to just kind of introduce the idea that not all sets are finite like that. You can consider whether you can even count the number of elements and count the infiniteness of it, so to speak. So there's just a lot of really cool stuff to do here. But as far as notation goes, I know some people don't like the ... But there is another way to this case, we're kind of trying to write out some of the elements. Of course, since it's infinite, you can't write out every single one, but you can also describe sets. So instead, I can say something like this. Okay, so I can describe an element. So an element X belongs in this set if X, so this is like all X such that X is even. If you have a little description here for the elements that belong in this set, that's called set builder notation, as opposed to trying to list out every single element, which would be roster form or roster notation. We can come back to this, but this is one basic explanation. Of course, this description is not very mathematical. You might want to use the word modulo. You can use the modulo function is what I mean. So you can use this description how you like. But this is just an example here. So we have X such that X blah 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 blah. Okay, we'll come back to another example of this in a little bit, but set builder notation, roster notation. And again, I'll write down some of these definitions and concepts in future videos, but just trying to cover some general ideas. Okay, so now that we have that idea, we can talk about, let's see, what should we do? Let's talk about the idea of whether an element is in a set or not. So this is just a basic notation thing. This means element of, this means not element of. So this little kind of curved E thing. So basically 2 is an element of the set 2, 4, 6. And 3 is not an element of 2, 4, 6. Okay. A little side note too. So here you can see 2 is an element. It is literally right there, right? It's an element of this set. This set has 3 elements. It has a 2 and a 4 and a 6 object. And 2 happens to be one of them. And 3 is not one of them. Our minds might look for patterns, and this is where if this is new to you, I just want to caution you to not look too much for patterns and rely on the notation itself. So for instance, you might see 2, 4, 6 and say, oh, that looks like some even numbers here. But for instance, 8 is not an element of 2, 4, 6. This literally means 3 objects grouped together like this, or not grouped. I'm trying to avoid the word group for collection because it's a different mathematical concept, but 8 is not an element of this set. You would have to describe the set of even numbers or include 8 or something like that to have 8 be an element. So try not to generalize based on any potential patterns here, okay? So element, not element of. So along those lines, speaking of the 2, 4, 6 being part of a pattern, we can consider the idea of a subset and a proper subset. So a subset just basically means like a part of a set. And so if I have 2, 4, 6, for instance, that is a subset of the set of all even numbers. So basically, if like a set A is a subset of a set B, then if I have an element in A, then it's an element of B as well. It doesn't necessarily work the other way around because B is like the bigger set, so to speak. So there can be elements in B that are not in A. But if A is a subset of B, then every element in A is going to be an element in B. I hope that makes sense. It's a sub, it's like a part, a subset. So you can write that more formally. But the difference between this as a subset versus a proper subset is that this is kind of like a less than or equal symbol. So you have the equal part versus just strictly less than. So technically B is a subset of B. So if you have an element of B, then it's it's an element of B. It's kind of redundant, but it still satisfies the definition of a subset, right? So we include the set itself, but a proper subset would not include the set itself. Okay, and so now that we have this idea of like a subset and a proper subset, we can also consider how when two sets are equal. I think this part is really interesting. So let's say I have a set A and it's just 1, 2, 3, because I'm just trying to focus on general concepts here, so we don't have to make the sets really complicated. But let's say I have a set A and that's 1, 2, 3, and I have another set B, and let's say it's 2, 1, 3. Are these two sets equal? Are they equal? Now this is where it's really interesting. So they have the same elements, 1, 2, and 3, but they're in different orders. Now A and B are equal sets. The order does not matter when it comes to sets because it's the same collection of objects. It's still just 1 and 2 and 3. The order of these elements do not matter. So A equals B. Okay. Now, here's an even more interesting situation. What if we have 2, 2, 1, 3, 3? Let's just throw one more 3 in here, like this. Now we have repeated elements. Now these are actually all the same. C is actually equal to B, which is also equal to A, and it might not appear like that because we have 1, 2, 3, 4, 5, 6. What appears to be 6 elements in set C. So a cardinality of 6, but we do not keep the repeated elements because our collection of objects are still just 1 and 2 and 3. We don't really care how many of each we have. So if you simplify this down into an actual set, it is 1, 2, and 3, or 3, 2, 1, or 1, 3, 2, however you want to order it. But the repetition does not matter. So in this case, A equals B, which equals C. Pretty cool, right? And this might be helpful to review if you haven't looked at sets, because a lot of people tend to forget this one. But in this case, they all are equal. So basically, they have the same collection of objects. So technically, when we write what a strict set is, you want the objects to be unique, and you don't care about order. So that's like a little detail here to mention, but it's a collection of objects that does not care about order or repeated elements. Okay, so that's how we kind of define, I guess it didn't define, but if we define equal sets, then we have the same collection of elements. We want to tie in the idea of subsets, and this is where there's logic fun that can come in, but if you want to think about the fact that if A equals B, then A is a subset of B, and B is a subset of A. Because of the if-then statements, and if it works both ways, then they are equal. Good fun here. So, other kind of operations or ideas we can think about are the idea of union and intersection. I'll do some exercises here, that's why I'm not too worried right now. I'm just trying to go through the general ideas and some notation. But union is basically when you combine sets together, you're basically adding them together. But because we don't want repeated elements, you kind of have to subtract out the extra elements, any duplicates. So a strict true union is not just listing one set and then listing another. You have to get rid of the overlapping terms. Speaking of overlapping terms, we have the intersection, which is the set of elements that are in both or multiple sets. So union and intersection. Okay, so again, for these are just ideas here. So as you keep advancing, these are just general concepts too that you can still apply. Okay, so I'm just trying to think of as much random set notation I can think of right now. When we talk about sets of numbers, you might see stuff like the set of real numbers, integers, which is z, integers that are positive, so you have a plus or a negative with a minus, the set of complex numbers, the set of rationals, so stuff like this. So this is just notation that we use to refer to certain types of sets of numbers. So these are all infinite sets, but you can do a lot more analysis with that. So like for instance, if you want to apply our set builder notation for rationals, let's say, and again this just comes up in different contexts, so you could say something like the set of x, so the x elements, such that if x can be written as p over q, a ratio of two integers, so you need to say where p and q are integers, so that would be z, and q is not equal to 0 because you can't divide by 0. So something like this. This is equivalent to the set of rational numbers. Any number that can be written as a fraction of two integers is a rational, so is a rational number. So this is the set using set builder notation, for instance. Okay, so there's good fun here. You can play around with it. And like I said, there are so many contexts. So like Venn diagrams, that's very satisfying to work with. So just basic logic problems, you might see them like on an SAT test, or like just reasoning skills for that. You have applications of this in like probability. If you want to talk about sets of possible outcomes, for instance, even in geometry, where, you know, I was just thinking about this one, but it's just a set. For instance, a circle. A circle is the set of all points that are equidistant to a given center, that distance being the radius. But that is what a circle is. A circle, by definition, is a set. If you extend geometry a bit, a lot more, you could go into topology, and this gets a lot more analytical, but definitely a lot of set work there. The idea of intersection, union, you can even just analyze whether you can count the terms in a set, or just like I said before, just how infinite exactly is the cardinality. Stuff like that. I'm not claiming to know everything, but I have seen this in so many different contexts at so many different levels. So it's a lot of really good fun, but I just wanted to make sure we're on the same page here. You might have seen me even use this word of a set just kind of in passing in different contexts throughout my channel, so just wanted to give an idea of what this is. I know it's easy to just kind of see the idea of union and intersection and be like, whoa, I know set theory, but there's just so many different layers to this. But I just wanted to introduce some of the notation here, you know, subset, proper subset, union, intersection. Kind of looks like I'm starting to draw some emojis here, but you know, whether sets are equal. We can get more into it. Like I said, I could just like make a little cheat sheet with some definitions, but and then all of our different sets of numbers. So I just wanted to do a little chit-chat introduction. I hope it was fun, interesting, nice review, something cool to learn, relaxing, if nothing else. If you're asleep right now, I'm wishing you sweet, sweet mathy dreams. If you're going to continue on with the rest of your day, I hope you got a tingle or two, and I hope that it's a great rest of your day. I'll see you around for more math and ASMR and math, and we'll just keep on jumping around, okay? Thanks so much for tuning in, catching this nice moment together here in our Math Nook. You're always welcome. Please subscribe if you haven't already, if you want to tune into more videos.